Welcome to Spring LIB.
This is kind of a, I think, kind of a fun problem. It's kind of explains some things I think kind of well. So what we have here is we got this bowl, and I'm assuming it's circular. It doesn't really need to be circular, but anyway, I'm assuming that it's roughly a circular bowl. And we have one side of it is rough, so we have rolling without slipping. And the other side of it is smooth, so we have rolling with slipping. And what the difference is that when you roll with slip, when you roll without slip, the velocity of the center of mass is related. The velocity, the translational velocity, and the angular velocity are related. When you're rolling with slipping, they're not related. They're independent of one another, because you could have something just spinning but not translating, or translating but not spinning, if it's a smooth surface. So they ask us, in this case here, how far up does this, if it starts off at a height h, how far up does it go over on the other side? Well, this is a marble, so the mass moment is 2/5 mr squared. So I'm going to say this is the gravitational reference down here. So initial energy at state 1 is mgh. At state 2, there's no potential energy, gravitational potential, and we just have kinetic energy, which is translational and rotational. Now, because we know that it's rolling without slipping, well, we know these two things have to be equal. And we also know that it's rolling without slipping, so we can substitute this into here, and setting these two things equal and canceling out m, we get an equation that we can then use to solve for omega. So that means we can find what the angular velocity is here. If we know the angular velocity, then we know the translational velocity too. So solving for omega, we get 1 over r times the square root of 10/7 gh. So does that make some sense? Yeah, because the higher you start, the faster it's going to be rolling down here, which makes sense. And then omega, or v, is just r times this, so that ends up being just square root of 10/7 gh. If it were just a particle, if it didn't have any rotational kinetic energy, then this would be 2. And so you can see that because it's rotational, has some rotational kinetic energy, the velocity is actually slower because some of this potential energy is going into causing the thing to rotate as well as translate. So if it was just smooth and slipping over here, it would be going faster down here. Now, when it comes up on this side, we have to say, well, what's going to happen here? It's rolling here. That's some angular velocity. And so when it comes up here, it's still going to rotate. It's still going to be rotating, as it rolls up here. It's not going to slow down. Its rotational energy, rotational velocity is not going to be slowed down, because it's just going to be spinning, but it's going to be translating. So we're going to have spinning and translating, but they're not related to one another. So what happens is at 3, and 3 is somewhere, wherever the height is, wherever it ends up. So at 3, we know we have 1/2 j omega squared as the rotational kinetic energy, and it's the same omega because we're assuming that it doesn't, there's nothing slowing it down from spinning. So it's the same omega. And then we have mgh prime, which is the height that it comes above the base here, which is what we're looking for. And that has to equal to the energy here at 2, which is, basically is the translational, okay, so what I did here is I plugged in j, and so this equals this, and then that equals the energy at 2, which is rotational kinetic energy plus the translational kinetic energy, just from here. Now we can see that this term and this term cancel out, because it's still the rotational energy doesn't change as it goes up this side. And then we can solve for h prime as 1/2 1 over g times velocity of the center of mass squared, which we know that. And so we get 1/2 1 over g times 10/7 g times h. And g's cancel out, 2 and the 5, get a 5, so we get 5/7 h. So it doesn't come back all the way up here. It comes 5/7 of the way back up to the other side. Now, if both of the sides were rough, then it's just going to come back up to the exact same spot. It's going to come up higher. And likewise, if both sides were smooth, it's going to come up to this exact same spot. And so they ask, why do you think that? Why do we think that? Why is this less than this? Well, why it's less than that is because even though it comes up to, there's no translational velocity when it comes up to this point, up to 3. Which, remember, we don't have any translational velocity at 3 right here. It's still rotating. So we built up some energy coming down here, some kinetic energy, but we didn't extract it all and going back up. We only extracted the kinetic part of it, and so we extracted less of it, causing it to rise up. But it's still spinning. It still has the same amount of energy, but it's spinning over here. So we would expect it not to rise up as high, because some of the energy that it had, that we gained as we came down here, some of the kinetic energy that was gained was not all lost in coming back up. Only the translational part was lost. So we'd expect it doesn't go up as high, because some of the energy is still in that this marble is spinning. So that's kind of the explanation, is that you didn't extract all the kinetic energy if this thing was smooth and this was rough. If they were both smooth, then again we'd have the same issue. We'd have it come up to the exact same side, because there's just no rotation period at all. If it wasn't rotating here, then it's not going to be rotating anywhere. It's just going to be sliding the whole time if both sides are rough. In that case, the velocity of the center of mass would be square root of 2gh, not square root of 10/7 gh. So it would be going faster here. Translational velocity would be greater.